Acid-base neutralization reactions. First we want to start by defining our acids and our bases. Acids are substances that when they are added to water, they will ionize, which means they will form ions. So they will ionize in water to form hydrogen ions, and those hydrogen ions are then donated to another species. So they're proton donors. Bases dissociate in water. So they break apart into positive and negative ions, usually to form hydroxides. Now, there's a broader category of bases that include things that accept protons. So, for instance, in the picture below here, we have ammonia, NH3, which does not have a hydroxide to break off of it. However, it does accept a proton and become NH4+. So that's what makes the ammonia a base. And then over on the right, we see three acids, our hydrochloric acid up at the top and nitric acid, both of which are what we call strong acids, which we'll get into in just a moment. And at the bottom, we have acetic acid, which is which is used to make vinegar. Basically, vinegar is a dilute solution of acetic acid. All right, comparing strong versus weak acids and bases. Well, this goes along with the idea of strong electrolytes and weak electrolytes. So a strong electrolyte is something that's going to produce a lot of ions in solution. So a strong acid or a strong base will break apart or ionize completely in water. So hydrogen chloride, for instance, that we saw before, when you put that in water, it breaks apart 100% into hydrogen ion and chloride ion. Weak electrolytes, or weak acids or bases, will ionize or dissociate only partially. For instance, the acetic acid, HC2, H3O2. So when you put this in water, it will only break apart partially into the hydrogen ion and the acetate ion. Most of this will actually stay in the original form, although this is where we've established that equilibrium, that balance, where some of the molecules will break apart, and while they're in solution, some of the hydrogen and acetate ions will combine back together again to go back to the non-ionized form of the molecule. It's important for us to learn the strong acids and strong bases. Once we learn the strong acids and strong bases, then we can just clump all the rest of them into a grouping of weak acids and weak bases. So we have hydrochloric, hydrobromic, hydroiodic, chloric acid, perchloric acid, nitric acid, and sulfuric acid. The ones that we should be familiar with, in terms of working in the lab, are sulfuric, nitric, and hydrochloric. Those are the ones that we'll see most often in the lab. In terms of strong bases, all of the group 1 metal hydroxides, lithium hydroxide, sodium, potassium, rubidium, cesium, those are all going to dissociate 100% when you put them in water and forming hydroxide ions and the metal ions. In the second column of the periodic table, you have calcium hydroxide, strontium hydroxide, barium hydroxide will form strong bases. All other hydroxides are fairly insoluble, which meaning that they will not dissociate to a great extent when you put them in water. So take a minute to take a look at these three acids, or pictures of these three. So we have HX, HY, and HZ. And as part of your homework, rank these in terms of acid strength. So put the strongest acid here, middle acid here, and the weakest acid farthest to the right. Identifying strong versus weak electrolytes. So the first thing you want to know is, does it dissolve in water? There are some ionic substances that will not dissolve in water, so those are going to be obviously non-electrolytes. The next question you would say is it ionic or is it molecular? If it's ionic, the question is moot, because if something is ionic and it dissolves, then it is definitely a strong electrolyte. So most substances that are ionic are going to be strong electrolytes if they dissolve in water. If it's molecular, now you've got to decide, is it an acid? Right? If it's not an acid, chances are it's a non-electrolyte. Things that aren't acids, when they dissolve in water, they don't break apart into ions. If it is an acid, you want to ask yourself, is it a strong acid or is it a weak acid? Strong acids are going to be strong electrolytes. Weak acids will be weak electrolytes. So there's some examples below here. Calcium chloride, nitric acid, ethanol, and formic acid. So you should also evaluate each of those so you can tell me when you come to class whether each of those is an electrolyte, a non-electrolyte. Well, if it's an electrolyte, tell me whether it's a weak electrolyte or a strong electrolyte or a non-electrolyte. Neutralization reactions. Neutralization reactions are reactions in which acids react with bases and neutralize each other. So here we have hydrochloric acid, sodium hydroxide, and you see that the products of this reaction are sodium chloride, a salt, and water, a liquid. So we have neither an acid nor a base here. The net ionic equation here, the sodium ions and the chloride ions are aqueous on both sides, so those are your spectator ions. So any strong acid, strong base would have the net ionic equation of hydrogen ions in solution reacting with hydroxide ions in solution to form water. The reaction below is a similar acid-base reaction, except in this case the base is in the solid form, which means that the magnesium ion would not end up being a spectator ion here. So the equation that you see in front of you here with the acid and the base, that net total ionic equation would also be the net ionic equation. Finally, we have acid-base reactions in which gases are formed. So rather than forming water, you can see that the acid, hydrochloric acid, and sodium sulfide react together to form sodium chloride, aqueous, and H2S gas, hydrogen sulfide gas. And here the chloride and the sodium ions would be spectator ions, so we would have a net ionic equation of hydrogen ion reacting with sulfide ion, forming the hydrogen sulfide gas. Below, we have the more common hydrogen chloride, hydrochloric acid react with sodium bicarbonate, forming carbonic acid, H2CO3, plus water. And in this case, the carbonic acid is not stable in water. It will quickly decompose into carbon dioxide and water. So you will not see the carbonic acid formed here. Rather, you'll see the bubbling indicating the formation of carbon dioxide. In the next video segment, we'll take up the talk of oxidation reduction reactions, in which we'll talk about the classification reaction known as single replacement reactions and get into the activity series of the elements.